Let me know if you have a trouble. And then for folks watching the recording, there we go. Yeah, it's looking good.
Okay.
We'll bring that up in a moment. Hi, GM. I'm Derek, the community steward at ETH Denver, aka Sporktow. Joined today by Tony Olendo from Polygon. Hi, Tony.
Hey,
How are you feeling today?
I'm good. I'm good. How are you doing?
I'm good. I see Beam Me Up Now has already joined us.
Mhm.
The regular. Good to see you again, Beam.
Hey.
Um, Beam, what's your level of experience with zero knowledge proofs at a conceptual level or at a technical level? And also, everyone else watching as you roll in, feel free to say hi or GM in the chat. I love to know which faces are joining us. Um, I'm excited because Tony is going to give us an introduction to zero knowledge proofs, and that fits in here on Theory Thursdays, where we try to give folks a level of, beam me up now, you put it well,
Yeah.
explain like I'm five type understanding, so that as you go to ETH Denver or find yourself in other conversations in some Discords, that you have some familiarity at a conversational level with some of these terms.
Yeah.
So we're going to dig into zero knowledge proofs, some of the backbone of how they work, and what kinds of use cases would make sense based on what they offer us as developers. So without further ado, I'll let you take us away, Tony, and then I may, if it's all right with you, just share certain questions that are coming up along the way that folks have.
Excellent. Yeah.
All right, let's do it.
Yeah. Well, yeah. Hell, hi, everybody. I'm not sure how many people are on. I can't tell, but yeah, GM, everyone. Really happy to be here. Really happy to be able to begin to just demystify this whole topic called zero knowledge proofs. Um, so, if you have zero knowledge about zero knowledge proofs, this is the main this is the presentation for you. So don't worry, we'll actually try to go through things in a very simple way that gives everybody a bit of context. um, so before I start, just a little bit about me. My name is Tony. A education solutions architect at Polygon, and I work with ZK Tech, and I build education curriculums over there. And today we'll start to talk about just an overview of zero knowledge generally, and what Circum is. I'll also introduce you to ZK Snarks, and I'll take you through a brief and a simple demo circuit that you could use. And all of this is just conceptual for you, just to understand. Nobody expects you to code, seeing as it is Theory Thursdays. So let's get started. What are zero knowledge proofs? They're basically a protocol that allows you that you know something without revealing what you know. And if you could think about that, think of like your driver's license. When you hand that over to any person in authority, there's a lot of information that is contained on your driver's license, like your address, like your location, and a bunch of other things. Um, and when you do that, you'll find that you have no control over the information that people have about you, right? Because you just handed over your driver's license, but there's no way for you to protect your privacy. So imagine if with zero knowledge proofs, you could actually begin to have a little bit more privacy, where you could more 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 uniquely begin to control some of your
Mm-hmm.
information, even as you spread it online.
Yeah, just to highlight what I think that's worth slowing down on. This is something that is new to
Yeah,
folks when they first hear it, but especially in the United States where the driver's license has your physical address where you live. If
yeah,
somebody is letting you into, say, a restaurant or bar that serves alcohol, and they only need to know what age, they don't even need to know what age you are. They just need to know whether that number is bigger than the legal drinking age.
yeah,
And along the way, they find out your weight and your physical address. It's
yeah,
very invasive. So it'd be
yeah.
nice to have a system where you could selectively disclose just the right amount of information.
Exactly, exactly. And selective disclosure is a real big part of some of the solutions that we're pioneering at Polygon with Polygon ID, and um, they actually they're actually really really important when you think about how we actually go online and what bits of information that we need to be able to share with ourselves securely. So let's just go through a simple thought experiment, right? So this is Alice and Bob, the famous Ethereum characters, Alice and Bob. So let's say Bob has a secret code, right? Um, and that code unlocks the door. And how does Bob prove to Alice that he has the code without necessarily revealing the code, revealing what the code is? And so they then come up with the thought experiment where they have two paths, and those paths are connected by the door. And if Bob has the code, then he could punch it into to either side of the door and pass through, and emerge on the other side. So Alice says, "Okay, fine. Um, I want you to come through side A the first time." And so Bob then goes in through side B, punches in the code, and comes out through side A. The first time he does that, it proves probability of like half and half that he probably has the code. Um, but then the more times Alice changes and says, okay, come out of B, come out of A, and if they do that 10 times, then the probability that um, Bob actually knows a code increases with every subsequent iteration of of Alice saying follow path A and follow path B. And this is essentially the way that zero knowledge proofs work on a rudimentary level, where without sharing the actual code, they're like parties, the various parties to this whole interaction essentially share the information they have, um, just by proving knowledge. And the beauty of all of this is that you could do this cryptographically without necessarily revealing exactly what you know. And so the successive times that Bob is able to come out of the right path, the more times that you could actually prove that this actually happens. Now, if you think about that, that's a very interactive way that Alice gains confidence, um, that Bob actually knows a code. And you could repeat this particular exercise, and you could get to like 99.97, percent assurance that Bob actually knows a code. Um, so if you think about like what the components of all of this, is that one, a zero knowledge proof is something that is complete. And so if the statement is true, the honest verifier will be convinced of this fact. So it has to be something that somebody actually believes is true. It has to be sound, meaning that if that at no point can Bob come out of the wrong path, because Alice will be like, nah, you don't know. So imagine if it happens once, the whole trust model collapses. And it has to be and the final component, that it has to be zero knowledge. And by that, we mean that you have to be able to confidently share just the proof without necessarily revealing the actual information. And that's how you kind of look at it. But if you look at further, um, uh, there are actually two parties to this whole transaction, right? So there's a verifier who verifies that Bob knows it, and then there's Bob, who is the prover, who proves that I actually know the code, but I'm not telling you the code. And so in concert, the ceremony that they actually go through to actually prove knowledge is actually comprised of two primary parties, which is a prover and a verifier. So let's think of like some actual use cases where this could actually be used, and you could think about it like in ways that would be novel. So how about if you think about authentication? If you go and you create an account at google.com or whatever it is, whatever site, they always you would be asked for a certain piece of knowledge, which is your password, that proves that you actually know, um, well, that you are the one who verifiably created that particular account. But as we all know right now, that doesn't provide the greatest level of guarantees. So we could actually have authentication that works in a way that we could verifiably log in to two different websites without having to prove I mean, without revealing a secret code or a password, but verifiably be able to satisfy the requirement of authenticity. If you think about its applications inside of blockchain technology, it's actually massive, and which is what powers like the ZK EVM. Where if you're thinking about roll up technologies, what essentially happens in Ethereum and the the novel, I guess, application of the ZK EVM is that we get a bunch of transactions. That if you have an optimistic rollup, it works differently. But in a ZK rollup, essentially, we get a bunch of transactions, and all of those transactions are pooled together. The states are transitioned right through, and a Merkle root is then produced that verifiably says that this is the brand new state of Alice's account. These are the number of NFTs as a result of this batch of transactions, and all of those could then be reintroduced back onto the main chain, which is Ethereum, and you could actually trust that all of those calculations are actually accurate because you're using zero knowledge proofs to basically summarize the brand new states that would have been affected by a particular group of transactions. So that's how they could be used in blockchain. They have a lot of applications in finance where you could verifiably send people funds without revealing who you are. There's a lot of applications in like machine learning and zero knowledge proofs where you could actually embed polynomial calculations to like machine learning models and come up with brand new novel applications, and even in voting. So if you think about voting, which is one of the most simplest use cases, if you think about it in the context of a DAO, a lot of DAO voting now happens on chain. There's very little expectation of privacy, and sometimes, depending on the voting system, you could actually tell who voted what. But we could actually counteract all of that using zero knowledge proofs and essentially be able to vote securely with a great deal more confidence than just somebody saying this is a blind vote. But the blind vote, but the way you actually voted sits on somebody's third party database, and you have to trust them that they will basically cover what you actually voted. So
Hmm.
so those are some of the challenges there. Yeah.
If I may, to zoom in on this voting use case for a moment, when I thought through zero knowledge in the context of voting, and somebody explained to me that if you have a system where every single vote is being recorded in a way where it is impossible to prove whether you voted for Alice or Bob
Yeah.
after you cast your vote, there literally is no record that you could show someone that verifies whether you voted for Alice or Bob because of the zero knowledge mechanism. You actually destroy the incentive structure behind like fraudulently buying votes, like in the example where somebody wants to pay me $1 million so that I vote a
Yeah.
certain way. If
Yeah.
I can't prove, I literally cannot prove that I voted one way or the other, then there's that much less incentive for them to try to buy my vote. So it
Exactly.
is an anti-fraud mechanism just as a nice side effect, which really blew
Yeah.
my mind to really think through.
Yeah. And I mean, some of the applications and uses of this technology, I think, would be the stuff of behavioral scientists to look at and kind of to just delve into and jam on, because
Mm.
they could change a lot of like our trust models and how they currently function across like democratic societies, in like from like DAOs all the way up to ballots, like national polls and everything else in between. I think we're only beginning to see what the application of like zero knowledge proofs are. And I think when I was learning all of this, somebody was saying, well, even if blockchain goes away, I think ZK is still going to stay, because there's just a lot more that we need to actually do and invest in actually building really strong ZK solutions. So, yeah, those are like really, really good use cases. Yeah. Um, Not seeing, can I get just a thumbs up from the people who are on? If you have any
Yeah.
questions, anything.
Yeah. Feel free to give Tony like a sweet thanks or like a, oh, hey, wait, I'm confused. Like all feedback is super useful.
Yeah.
There's a reason we're doing these live. It's to create that much easier of an opportunity for y'all to ask follow-up questions, or we can go down a particular thought experiment if you like. And I'm watching the chat, so I can shout out if anything's happening like that.
Excellent. All right. So I'm just going to keep going. So let's look at like the ways that you could actually construct proofs. You have ZK snarks, um, which essentially provide a great deal of security, but because they needed a particular type of setup, you have to have like a trusted party event where you have different people coming in, and the more people you have who could share the secret and then destroy it, um, the more secure it actually becomes. And I think I was seeing something on Manta Network where they had the largest trusted party setup with 1,600 people who came together to generate a proof. And that is just virtually impossible for you to ever know what that witness is. But those are some of the like the novel applications, and then you have ZK stocks, which work almost I think recursively. And so what the huge benefit of using ZK stocks is that ZK stocks likely are quantum safe. So if you have like quantum computing, ZK stocks should survive. ZK stocks not so much. And you have bulletproof, and there's so many other different types of proof construction mechanisms. But today we're going to be focusing on ZK stocks, and let's make
Wait, can
that.
we go back and because we're defining these, right? And these are
Uh,
acronyms, right?
yeah, these are acronyms, but I'm only going to focus on the first one, which is ZK snark, and then I'm going to define it in the next slide.
Oh, you are going to define it.
Yeah, for sure.
Oh, okay, great. I just wanted to make
Yeah,
sure we
so this is
explained what,
just
like, where did snark come from? And so we'll
yeah,
get there.
exactly. Totally.
Okay.
Yeah. So what does snark mean? So ZK, as the name would suggest, is basically zero knowledge. A snark refers to something that is succinct. So the proof that is generated is very, very short. This is ideal because it means proof could be stored on chain. I think it comes to like 32 kilobytes or something like that. So do not quote me on that. I need to confirm that information. Might be a bit out of date, but they basically produce a really, really small proof. Sometimes with stocks is that they produce a fairly large proof, and if you try to store that on chain, it's a bit harder. It costs more gas and all these kinds of things. So stocks are kind of like favored for like blockchain applications, and it just means that what is produced, the proof that is produced, is really, really short, and the non-interactive component is basically allows the verification to occur without sending messages between the proof and the verifier. So if you think about like our initial analogy, um, we had what's it called? Alice and Bob. Yeah, we had
Mhm.
Alice and Bob. And the way that Alice gained confidence about Bob's knowledge was that no, they had Bob had to jump through a set of hoops, and with every successful iteration, she gained more and more confidence. Right. So what happens if we could replace that whole ceremony with just a cryptographic proof or a mathematical assessment that verifiably and guarantees that yeah, Bob actually knows the code, and if he didn't know the code, then this whole math equation wouldn't result in X, right? And so when zero knowledge proofs initially came out, there was a lot of discussion around what that looks like, and all of the ceremonies are like, well, the all of the proof construction mechanisms that existed at the time, you had to have like a lot of interaction between you and them, and it became a whole thing. But then uh, the non interactive stocks kind of emerged, and they became like really, really useful. So and the subsequent applications with God 16 and a bunch of different other similar technologies that really helped. And then the argument is that the A, which is the argument, is just essentially that is what we use to provide the knowledge. Um, we actually use to pass in the inputs and the various bits of information that we use, but they're not quite mathematical proofs. But there are arguments that we actually introduce to be able to power the generation of these particular zero knowledge proofs.
Before we move on, I guess just to, I know we're like really trying to reduce quite complex ideas to simple terms, but you're saying non-interactive, and I can see the appeal of there not having to be a back and forth between a prover and a verifier. But
Yeah,
there is at least one, because in the argument you're saying we're sending some kind of message, like
yeah, you're
Bob
sending.
has to go through a door. So
Well,
are we reducing it to like one interaction? Is that a fair way to describe it?
you could you we're reducing it to a calculation so that when Alice comes to verify, she would only need to run it once, and if she has the public input of that particular transaction, she could go and open the door herself without necessarily knowing what the secret is. So there's public and there's private inputs, but essentially that's essentially what we actually say. I'm
Okay.
not sure. Yeah,
I'll let you keep going to provide more context.
cool. So before we go further, I'm going to introduce Circom, and Circom is a circuit programming language that we use to develop circuits, right? So um, and we use Circom to develop like arithmetic circuits that eventually become the zero knowledge proofs that we use, right? So it's a programming language just like any other, um, and it has a compiler, and you could create your own arithmetic circuits using it. Now, the way that you would need to think about developing with Circom specifically is that there's a difference in terms of how computations are actually arrived at, right? So if you think of modern computer science today, most modern programming applications are based off of a Turing machine, and the Turing machine would be a kind of like a VM or something of that sort that essentially performs any form of calculation without any kind of limit. So if you think of like the EVM, is a Turing complete virtual machine where you send transactions and it could perform any kind of calculations or computations bounded by gas. So the thing with Turing machines is that they're not particularly ideal for zero knowledge proof applications.
Hmm.
They are more suited. So arithmetic circuits are more suited for zero knowledge proof calculation because they work off of just very simple um, mathematical operations. So you could just subtract, add, multiply, um, and divide, and you could do that around logic gates. So I don't know if you know more about logic gates, but the closest thing is if somebody in the audience has an electrical engineering background, it's easier for them to understand like zero knowledge proofs in the context of, I mean, the arithmetic circuits um, in the context of like a signal is produced, it's sent, and signals either pass through certain gates, which then determine like the eventual output, right? And if this doesn't make
Mhm.
sense, don't
Well, I
worry.
think let's define a logic gate so that somebody who's never heard of one has a mental model of what we're talking about. Would that be useful?
Yeah, I would say that. Yeah, so a logic gate is one that when it receives a particular input, it performs a deterministic application and produces an output. So if you think about
How about like an AND? So the AND gate is looking for two inputs, an
two
A and a
inputs,
B, and it
yeah,
will check both inputs. If you have no idea what I'm talking about, imagine a light switch, and the
yeah,
light switch for input one is either on or off, and the light switch for input two is either on or off, and then there's a light on the other side of this AND gate. That light will only be on if both light switches are in the on position. In other words, the switch one and switch two are in the on position. So
yeah,
in this way, we've got the AND gate, the OR gate, the neither of them gate, the only one of them at a time gate,
yeah,
and so on.
yeah, exclusive or all kinds of different gates that you could actually go through. But so when you actually think about designing zero knowledge proofs in terms of circuits, it's kind of like a different paradigm from your traditional like object oriented programming and all those things. Like this is a, well, not object oriented programming, but essentially like your Turing complete type of programming where um, the way that you tie together your inputs and your outputs could be loosely coupled. That's not the
Mm.
case with zero knowledge proofs.
Mm-hmm.
Yeah. Um, and the other piece of this is Snark.js, which basically allows you to generate zero knowledge proofs on your browser using like the Grot16 protocol. So the library includes tools that you could like use to set up like multi-party ceremonies where you could generate snarks. And this is where the criticism about snarks are, is that oh cool.
I'm just laughing because so many new words showed up on one slide, and this is like a great turning point of like where, I mean, we definitely don't need to go into the history of all the terms, but like
Yeah.
I literally see the universal powers of Tao ceremony as something written here, and as someone who doesn't know what that is, I'm like, that sounds super cool. Like, what is this?
We'll go
So
through it.
I'll let you keep going, but I'm just definitely
Yeah,
playing the beginner here because I do
yeah,
not
yeah,
know very much about these. So
yeah,
I'm acutely aware of when we like jump to a bunch of new stuff.
yeah, yeah, definitely. And this is part of like that whole thing. So we're gonna go through what all of this is. I'm just basically giving you like just base definitions, wax on, wax off, and then we'll bring it all together in the end so that you could get what it is. But
Okay, Mr.
basically,
Miyagi, go for it.
yeah. But basically, Snark.js allows you to be able to generate zero knowledge proofs online. And Powers of Tau ceremony sounds really, really cool. I agree. Um, so this is basically what the process looks like. Um, and so at a high level, you design your circuit using Circom, and you could use your own code using Circom, or you could use like some of the safe templates. And these are primarily derived from the Circom lib. So there's a group of templates that exists on Circumlib, and there's a uh, the entire libraries that do that, and we could reuse. And I guess one of the coolest things with all of this technology is that you could actually circuits or basically templates are composable, so you could use an existing template to build on another template and another
Mm.
template, and you could build more and more complex zero knowledge
Oh,
circuits.
so we don't have to repeat ourselves, and somebody
You don't
does
have
all the
to
heavy work of figuring
repeat
out how
that.
to do some kind of a system, and we can reuse that without having to do
Yes,
the circuit diagram over and over and over. Oh,
basically.
okay, great.
If you want to do like a zero knowledge circuit that verifies like your ECDSA signature or something of that sort, you could simply you could simply reuse the existing ECDCA template and keep it moving. And then from there, what we do, so once you finish designing your circuit and it looks okay, you then compile it. Um, and compiling the circuit produces something known as the rank one constraint system. I have an article that I pushed out today. So if you're interested, it's like a 12, 13-minute read, which goes into a lot more of these details in a much more palatable way. And so if you're feeling bewildered or like just lost, don't worry about it. Um, just read the article, I guess, where you could understand a lot more of the background. And I'll link it to the tweet here at some point. But if you just check like my latest tweet, you should find it. Um,
I found
um,
it.
you found it? Excellent. Yeah. Yeah, so it's on Dev 2, and it's a part two of that. Yeah, if you could share it here, it would be really great. But basically, once you go through the first step, you compile the circuit, and then you use the circuit. You then use Snark.js to compute a witness, and the witness basically produces a input and a witness JSON file that you then now use to generate a trusted setup. And ideally, the trusted setup isn't something you're doing alone. There are multiple other computers available, and that or other persons that you could generate a witness. This like in production. That the more the merrier, and you could generate a witness and um, or generate a trusted setup where you introduce your witness, and then you then uh, you then create the setup, and then you create like the proof. And after that, you could validate it, And once you validate it, basically you're just checking that given a particular set of inputs, it gives you a particular output, right? And from there, um, you could you could generate a verifier, which generates like a Solidity file that you could then put on chain. That once you send files to that Solidity file, it has all the information you need. And so you're basically coming from the circumcompiler. You go into Snark.js, which generates a witness. So you and in the witness you have a proving key and a validation key, and the validation key is used to generate like Solidity code, and you have a compiler that generates like your zk Snark proof. I'm hoping this is simpler than the strict definition of what.
It is, especially as we look at the bottom half of your diagram and people
Yeah.
walk away hopefully understanding what, regardless of how the pieces get created, if we can understand the properties of them and what it means to interact with them. Like you said, zero knowledge technology does not have to run on top of blockchain infrastructure. But one of the things that is nice about having the verifier code run, for example, in Solidity, for example, on Ethereum mainnet or some other EVM chain, is that you inherit this trust minimized, decentralized nature of the computer itself. Because if you're running a verification code on some centralized server, well, you don't know maybe whether the message has been tampered with on the way there, on the way back, the code that's over on the server end. So it's nice to be able to have not only the operation you're doing, which is sending your proof to the verifier, be secured through like the zero knowledge architecture, but also the process of sending your message there and getting it back is something that you have a greater degree of trust in, that you inherit from it running on a blockchain computer.
Definitely.
Like, because isn't it true that we could deploy that verifier code to like AWS?
It needs to be like, so it generates a Solidity file,
Oh, it's okay. It's
and this
EVM.
is, yeah, this is just for that particular purpose, but you could repurpose it in any way to generate any other type of file that you need. Yeah.
So Snark.js compiles to Solidity.
Okay. Yeah. Specifically.
Oh, okay.
Yeah.
Okay.
But it's not like there are other applications if you want to host this in a different in a
Environment.
different platform or something of that sort. And I
Mm-hmm.
think even WebAssembly is supported, so you could do that there.
Okay.
Yeah. Um, so I'm just gonna go over from this point onwards. Once you guys have like just a general overview, and you don't have to understand everything now. It took me the better part of 6 months to get to a place where I could actually do this presentation. Um, so um, this is just like a general information and overview segment, and so I'm going to go into a couple basic features of Circom, how it works, how we kind of bring things together, and show you in the end just a basic code walkthrough of what that Solidity file looks like once it's generated and how simple it is. Hopefully, it becomes simple. So we already spoke about like what the electrical circuit is kind of running in parallel to like an arithmetic circuit, and basically they just allow you to define computations and express them as circuits that have inputs. They have constraints, which are the wires through which like the signal passes, and you have an output, which is the light coming on, right? So if you think about your home, it's a simple system that basically has like inputs. If you have like a two-way light, um, so a light that could be switched on from any point, there's different ways that there's an actual circuit that runs through the board that ensures that when you flick the switch, it actually turns on. And there's just very basic inputs. There's constraints, which are wires, and an output, and all of those are kind of tied together. But the main piece where a lot of developers struggle with, when they start jumping into Circom, is you have to learn how to express like a computation as an algebraic equation. And in Circom, basically, you could express these as quadratic equations, as linear equations, or as constant equations. But specifically for the generation of constraints, you have to use quadratic expressions. If that doesn't make any sense, don't worry about it. I have a simple example that shows what this looks like, hopefully soon. Um, but if you think about how the arithmetic circuit works, is that there's a private input, there's a public input, and then there's a state deterministic program that ties together what the output looks like, right? So, and another way to basically express that is you could think of the kind of circles as logic gates. So the circle that you see in there is like a logic gate, that it multiplies. You have another one that adds, and you have signals. And you could say A and B are public signals, C is a private signal, and D becomes a temporary value that holds the value of A times B. So you could define public signals, you could define private signals in a circum, and you could define intermediary signals that exist inside of your particular circuit, and all of these could be tied to a particular output that that exists within a set of constraints, a set of quadratic constraints. Um, and if you think about that in algebra, I'm just taking you back to high school math here. It's basically a quadratic polynomial of degree 2. And it has one or more variables in which the highest degree term is of the second degree, right?
Like a parabola.
Basically, yeah,
Come on, you got to bring it all the way back. It's y equals x squared. It's a parabola.
exactly.
Okay, great.
Yeah,
Or maybe it's like a fancy parabola, like y equals x squared plus 3x minus 2 or something. But the highest thing is like an x squared term.
it's
There's no
x
x
squared.
cubed term or higher.
Yeah. Well, it's the constant, the coefficient that matters there, but yeah, um, that's what determines like the term.
Okay.
Yeah, but yeah, essentially.
Are you
Uh,
saying if it was like 5x squared, it would not fit this definition?
no, it would
Okay,
totally.
so what
Yeah.
did you mean by the constant term matters there?
Oh no, it's the no,
The like
I'm
minus 2 I said.
sorry.
I'm sorry. So what would be an example of a algebraic equation that does meet this in like high school math terms?
Um, Actually, really simple. I would actually go back to A times B plus C
Okay.
equals 0. Like really simple.
Okay.
Yeah, and you could replace A to be like two 2A and 3B for, yeah, really simple math, which is where we actually go. Yeah, which is why like I deliberately try to keep it as simple as possible, even in like the articles I wrote and all those things,
Yeah.
so that it's absolutely
Definitely.
accessible.
You can't please everyone. Andre, who's listening, really appreciated that we dug into what a logic gate is and defined it. So I was attempting to dig into like what's a quadratic equation, and he
Yeah,
was like,
that's
"Oh, okay,
where
no math, you
that's
lost me."
where
So
he draws
we'll
the
just
line.
move on. I'm
That's where
sorry.
Yeah, that's where
Quadratic
he draws
equation.
the line. It's like quadratic equations. Yeah.
Okay.
So let's look at how you would express this. So if I give you JavaScript or any other programming language, you would express, and I want the value of y to be 7 if it is less than 5, but otherwise I want it to be 9. Now, in any other programming language, this is how you'd express it, and it would be really simple. Um, but if you think about it in terms of a quadratic constraint, essentially what we're doing here is that we're expressing this as 7 times x, which is if x is less than 5, then it's whatever it is. Oh, no, if it's less than 5, it will evaluate to 0. 7 times 0 is 0. And therefore,
Oh, the green parentheses are just evaluate to 1 or 0, like a
yeah,
true false. Okay,
yeah,
cool.
yeah. And if it is that 9, well, if it is greater than or equal to 5, then it would evaluate to either a 1 or a 0, right? So simple logic gate, but this is how you would kind of make it simple. I'm hoping this is as direct as possible for anybody looking at
Did you
following.
say as direct as possible?
No, as
Oh,
direct.
direct. I thought you were
Yeah.
making fun of me. That's great. My mistake. I'm hoping
Yeah.
this is as
No,
Derek
no.
as possible. We should start saying
Yeah.
that.
We,
Okay, so just to highlight it,
That
I've
could be
never
a
seen
check.
this syntax. Sorry, I interrupted you. Go ahead.
Yeah, yeah,
This green thing here, I initially thought it was saying 7 times, and then if x is less than 5, whatever that is. For example,
yeah.
7 times 4.
Value is
But it's
the
not that. It
yeah, yeah.
evaluates to
One
1
is,
or 0.
yeah, 1 is 0. Yeah,
Okay.
yeah, um, yeah. So exactly, Andre. Yeah, and so this is how we kind of like express things as a quadratic constraint. And I'll go through um, a better example. Well, a more practical example of what this looks like in the subsequent. Well, where we do like a basic code review. Um, and if you look at this, this is another example where you're saying essentially um, if uh, if it's a draw, then p less than 1, or this wasn't formatted and I was supposed to change this. My apologies. The
I forgive
formatting is
you.
a bit off. Yeah, yeah, formatting is a bit off. But basically, the value RET will evaluate to either 2 or 1, depending on if it is less than the winner, right? Um, this is how you would,
Oh, okay. Sorry. Yeah, you hit me with the ternary operator, and I just like
yeah,
got to really slow down. So, can you walk me through? So, RET, of course, is short for return here, as in
yeah,
what I'm
return,
giving
yeah,
you back.
or
Can you walk me
return.
through both return lines step by step, please?
Yeah. So if so this is just a code. This is just a code example. You could ignore the first one there that says if something is a draw. Um, but oh, sorry, if it is not a draw, okay, then let's find out. If somebody is less than the winning value, then um, I want to find out if is p1 is less, um, then assign, if it is false, sorry, if is p1 is false, then assign the return value to be 1, or else if it is true, then assign the value to be 2, something of that sort.
Okay.
Yeah,
Are these two lines not?
they're kind of redundant. Yeah,
That's what I'm wondering.
yeah, they would be.
They're both in the if statement, right?
Yeah, they are. They are.
Oh, cool.
Yeah.
Because what I'm reading is return is P1 less.
The
If
ternary
that's
would
true,
return.
then
The
we
ternary
set
would
return to
return.
1.
Yeah, this is the best example.
Okay.
Yeah. So, but we'll go through where I got this from, and you'll see the logic a bit better.
Oh, okay, sure.
Yeah. Uh, so in in circum, we would define, if you were to do like a similar check, is that we define a signal as a p1 check, which checks the value, and then we would assign um, the value if player one is -2, and I will be going through like the full example later. So for now, I just want us to see there's a there's a polynomial constraint here where we have a multiplication and a constant there that are all constrained by the value 0, right? And all of this is being assigned to the P1 check, right? And if you have more questions about this, there'll be a brief code review where we'll actually go into this. But this is basically doing more or less the same thing as this is supposed to be doing.
Got it. Sure.
Yeah. Cool. Um, so some basic features of Circom. There's a pragma, and the pragma basically tells the compiler what version of Circom to use, and that's like at the top. So if you use pragma in Solidity, it's more or less the same thing. There's signals, and signals could be defined either as input, as an output, or an intermediate, and those would be private by default. Inputs are made private, are public, meaning that you could actually receive the input from outside of the circuit, and then the output is what is essentially generated when the value is being passed out as the final complete value. And they could also be arrays, so you could be uh, they could also be defined as arrays, and you could perform like your standard array calculations, just like in any other language, using um, an array that you receive. Variables also exist, and these work the same way that you actually have. And the biggest difference is that variables allow you to hold values that you don't want to tie to an actual constraint, but are holding like temporary values inside of your particular application as you're moving along, right? And these aren't signals, but they're basically temporary holds that you use for storing values. So they could hold numerical values, and you could use them to build actual quadratic constraints. Um, and so they become the building blocks of your eventual quadratic constraints. And the thing with like a circum circuit is that circum requires you to include an actual quadratic constraint for it to actually compile. Um, so that's how it essentially um, compiles everything into a zero knowledge circuit. And then you have templates. Templates are basically objects that you could reuse, and they are instantiated using the component keyword. So if you define a template, like the one that you're seeing on your screen here to the left, um, there's a pragma that is defined. You have a template. You have various inputs, and you could see that we eventually assign it out to that, to the out value, which is what is outputted, and anybody else who would come to consume this would then pass in a value, and you could reuse this elsewhere inside of your code. Um, so that's how you consume a template, and basically they used to define a brand new circuit, but they could also be used in a composable fashion in other circuits as you kind of move that along.
Hmm.
And from a doc standpoint, I'm not sure how I'm going to share this with you guys right now.
They're not super long. People can just type them, and they can watch the recording or screenshot or whatever.
Yeah, definitely. Um, and we'll go through. Yeah, so if you want to understand more about Circom, there's a lot more in the documentation that tells you more about how it's supposed to work and different things. You have the Circom library, which has a lot more templates that you could use to see um, just what the syntax look like, what the best practices are. And a lot of those circuits have been really foundational in the development of more complex zero knowledge applications. So when people have gone on to build applications, the basis of the templates that are available. Snark.js, as I would have mentioned, is used to generate a witness and eventually compiles all the way down to a Solidity file that you could then put on chain. And the ZK Hack Whiteboard series goes into a lot more of the math behind the zero knowledge proofs, and there are a series of, I think, 15 videos right now that were produced by Polygon in conjunction with various other people that you could review and just learn more about zero knowledge um, from a math perspective all the way to complex topics in terms of how they were used in the ZK EVM and various other points in between. Before I move on, just wanted to pause there if, in case anybody had any questions.
I have a naive question.
There's no such thing, but yeah, go ahead.
Well, it's a good example of a question that I would get all the time as a high school teacher, where it's like, I think I'm connecting two things, and then you'll either say I don't know or no, that's not at all. Those two things are not connected. In the beginning, you gave the example of Alice telling Bob which of the two paths to come out of. And
Yeah.
in doing that, Bob could show that Bob had the ability to go through the door and choose which path to come out of. In other words, there were two solutions. There was like A and B.
Yeah.
And I noticed that there's this quadratic constraint that's necessary to compile the things that are being set up in this language. And I what I remember of quadratic systems is that they except in the cases where they have no or one solution, usually have two solutions. And so a part of me is wondering if the quadratic constraint is, at a very simple level of explaining it, the mechanism by which there are sort of multiple solutions or multiple paths that can be gone through, and it is only by having this secret or this code that you can reliably prove, like, I can come out of either door, or I
Yeah.
can come out of either path.
Yeah. Essentially, that's exactly it. So you're connecting things correctly.
Oh, cool. I think
Yeah.
I could explain that to a 12-year-old. That's cool. All right.
Okay.
Sick.
Then my job here is done.
That we got it as direct as possible.
Yeah. Great. Yeah. 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 That's a really good example.
Okay.
So let's go through just a simple circuit.
Let's
Um,
crank that text size, Tony.
yeah, definitely.
Uh-huh.
Uh, let
Maybe
me
like 5 more. Uh-huh. 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 That's good enough. That's too much.
use this. Right. Um, so I won't go through all of this because we genuinely do not have the time. Um, I'll just go through a basic overview, but this is like a rock, paper, scissors example. Oh no, this is the wrong one.
It's
Um,
literally called RPS wrong.
yeah, it's actually called. I did this because I got myself in trouble once before.
Okay.
And yeah. When I have more time during this presentation, I kind of go faster and get into the code and do more explanation, like of the code line by line.
Okay.
Um, and I needed to. I usually show like this is how you do it if you're a regular developer. This is how you do it as a ZK developer. And I
Mm.
always used to get like the rock paper scissors wrong as the right, just like I did right now.
Got it.
And so that's future proofing me. Um, but
Great.
yeah, as you can see here, so we have the pragma at the very top. You could import an existing circumlib. So we use just npm to pull in the circum library, and this is the comparators circum library that you pass in certain values to. Um, you then define the template, and the template, once it's defined, you could define your signals. And remember our whole analogy around a electrical circuit, right? So you have the inputs. So this is the player one and the player two. And then you have the output that tells us who the winner is. And if it outputs zero, then it's a draw. If it's one, then it's player one, and two is player two. Simple enough.
Okay.
Yeah. Um, so this is how you're gonna come in and begin to check like if the constraints. Um, Basically, you first come and check if the value is it matches your well, the value could only either be, because part of the whole design of this whole system is that you could only pass in a two, a three, or a five as your turn. And two, if I remember, where did I put
Why
that?
did you pick 2, 3, and 5? These are
Uh,
crazy numbers to pick. Did it make
I
the
think,
math easier?
well, I just needed it to represent the different states. So either two is either rock, three is paper, and five is scissors or something like that. Or
Okay,
maybe
if we were starting over, I would pick 5 to mean paper because it's 5
five to mean
fingers,
paper. I think it
and
makes sense.
scissors
Yeah.
is 2 fingers up, and rock is 0. Is 0 allowed?
Zero, no, because zero, I'm actually outputting zero to indicate that nobody won.
But then how are you allowed to use 2? Because that's also an output that indicates
Yeah,
something.
actually, yeah. Well, they're not particularly tight. So those two are
Okay,
different.
great. So we could use 0. Does
You
that mess
could.
up the math, like multiplying by 0? Something like
No,
that?
no, because
Okay, okay.
the
I
input that we
I'll
see.
do a pull request later.
That totally makes sense, and I might be inclined to review. I mean, to actually approve your PR, but who knows? Who knows?
Oh, sure, sure,
I
sure.
have comments as well.
Got it.
Yeah. So yeah, I'm not gonna go into like the specifics of this, and I'll post this in part three, which I'm releasing next week. But basically, we are using math to constrain and make sure that we're returning a value that is either two, three, or five, right? And we're using the comparator there to be able to assign that. And we do the same for part two, and this is where we actually define the actual state. So if I was to refactor this, I'd probably move this up and change these variables that are internal, and
Mm-hmm.
change this to like raw.
Mm. Mm-hmm.
Make it easier for people to understand.
Definitely.
I think I'll do that.
Okay.
Um, and from there, you could define like the various states, and you could multiply the various values to be able to come and make sure that they are zero. But um, I know we have like 4 minutes left, so I don't want to go over, but basically, this is a comparator that checks if a value is zero, right? So we give in the output and we subtract another value there, and it checks, basically tells us if it's zero, and we assign that value here. So the out of that value is what we assign to this signal that we defined just there. And without going into all of the details, at the very end here, we have the final calculation, and we introduce the constraints, and essentially we tie everything, comes down to this particular constraint that we have at the end here. That it evaluates uh, to evaluates to 0, 1, or 2, 0, 1, or 2, depending on what the value that is.
Wow.
Yeah. Um, and from there, there's a whole process, right? So once you've defined your circuit, so if you remember the presentation, once you defined your circuit, which is the first step, then you go into the rank one constraint system. And if you look to my left here, um, there's a rank one constraint system. It's a huge binary file that has, so you generate your constraints, and then you produce a verifying key and a proving key. Yeah, proving key. Uh, so these are commands that you just keep running, and I think I have them all here. So you define like the rank one constraint system, then you start a powers of tau ceremony, which you could review the docs. Um, then you generate a key, and then like this, the DX here absolutely sucks, huh? So
Sure,
what you
sure.
eventually end
Why
up
aren't we
doing,
rolling up all 10 of these steps into like
I have,
SOCOM
yeah, like, I have
compiled?
a script. I have a script, and
Okay, great.
there's people,
Great, great, great.
and there's a team that already sorted this out.
I mean, when you're at a place where
This
the
is a low
fourth
level
thing
thing
you're doing
I'm
out of 10 is like, and then you start the powers of Tau ceremony.
Yeah, it's really annoying. It's really annoying. Um,
I
yeah.
love it.
So as you can see, like on different repos, I just have these running as a command, and I did like a simple bash script that does all these things. But the main thing you want to do is you could do the verifier. The most important part is that you actually verify. You actually verify your your zero knowledge proof, and it generates a solidity file, and then you could generate sample call data, which you could pass to um, that particular function. So let me just show you the verifier. Um, and the verify function, basically the file is huge, a bunch of things that I personally don't understand. But the
Sure.
thing, yeah,
This is
like
where you stop understanding things?
this is just to
Everything so
tell
far you were good?
I was good. I'm fairly
Okay,
good.
okay. It's good
But
to admit we all have limits.
yeah, there's a lot of pairings and like points and like different things that go into this particular smart contract. But the good news is all you need to do is find this public um, this verify proof function. This is all you need. And if you pass arrays to a solidity function, you could write zero knowledge proofs. That's how simple it is. Um, so
That's how simple.
anybody, yeah. If you could just generate and pass an array, then you're able to pass, and it will tell you whether or not the proof is valid. And this is the only thing you call with given data. Now, if you had the call data, um, if you generate the call data, it will give you like what needs to be passed, and you could test that. And then you could now work on different iterations of what that looks like, why it wouldn't be ideal, so on and so forth. Um, but yeah, this is just, hopefully this has been a sufficient overview that's taken you from knowing nothing about zero knowledge proofs. The goal here is just to you for it to be a little bit more demystified, and you could have a clearer path of what it would take for you to actually become a zero knowledge proof developer. You now know what Circom is. You now know there's a language that uses that zero knowledge developers use, and you know there's a horrible developer experience that enables you to generate a
Powers of
solidity.
Tau ceremony.
Yeah.
Yeah, and the even if you don't end up becoming a zero knowledge developer, you're aware at a conversational level of some of what it offers as like a paradigm and as a infrastructure, and then also to just appreciate how hard working anyone that's still at this very early stage trying to get their hands dirty and create some of these building blocks for future generations of developers to come in and stand on a better DX. I just have a lot of respect for people that are in there just making it happen right now.
Yeah. Yeah. Definitely. All right. Cool.
Well, thank you so much for joining, Tony. I definitely learned a lot, and I think this one's worth a rewatch. And want to appreciate you. If folks want to get a hold of you and ask any follow-up questions, where can they find you?
Twitter or Telegram. Tony Olendo.
Okay.
Yeah.
Great. Tony Olendo. Thank you so much. Is there any final words of wisdom or anything you want to encourage people that are on their learning journey, whether or not they're at linear algebra, masters in engineering, or just really curious about this Web3 stuff, like that you would like people to take away?
Yeah. So if you're curious, like the only thing I'd say is, yeah, being involved in blockchain for me in this way has been, I guess, part of the most fulfilling part of my career, and I've been a developer for 13 years. Just because everybody means well, and people are working towards building a decentralized future, and different philosophies about what that looks like, and there's very strong opinions. But at the end of the day, this to me is a better use of my time and my energies, and so um, um, this it is a high conviction path, but it's very deeply rewarding because of all the friends you make along the way.
Well said. I might clip that. I really enjoyed that. Thank you so much, Tony. I really appreciated you having you on today.
Yeah, same here.
All right. Everyone have a great rest of your day. See you on the next one. Tomorrow, raise your sporks. The road to ETH Denver. We are continuing to talk about the details of what you need to know to participate in the Biddle-a-thon, like prizes, bounties, mentors, judging, and so on. I really look forward to seeing you all there. Until next time, bye.